So first, the requirements for estimating a population proportion P. First, the sample is a simple random sample. Second, the conditions for the binomial distribution are satisfied, which means there's a fixed number of trials, the trials are independent, there are 2 categories of outcomes, and the probabilities remain constant for each trial. Third requirement is that there need to be at least 5 successes and 5 failures in our sample. Under these conditions, the sampling distribution of sample proportions can be approximated by a normal distribution. Now, the way we use that fact is that we use a Z-score, which is from the standard normal distribution, to distinguish between sample proportions that are likely to occur and those that are unlikely to occur. A Z-score on the borderline between these two is referred to as a critical value. So here's a picture of our normal distribution, our standard normal distribution. So we have a mean of 0 and a standard deviation of 1. So our critical values are going to be the ones that are on a borderline between sample proportions that are likely to occur and sample proportions that aren't likely. So anything in between these two would be the ones that are likely to occur. Anything in those 2 tails is going to be something that's unlikely to occur. Now, we'll need to find those critical values in order to construct a confidence interval. So if we have a specific confidence level, here's how we find our critical value. The alpha is the probability that the confidence interval does not contain the true population proportion. In other words, alpha equals 100% minus our confidence level. Then we take alpha and split it equally between the 2 tails of our standard normal distribution. The critical value negative z alpha over 2 is the cutoff value for the bottom alpha over 2 of the z-scores. So here's a picture of what we're doing. Here's our confidence level. We want that to be the probability that our interval does contain the true population proportion. So the complement of that is going to be alpha, and we're going to divide alpha equally between the 2 tails. What we're looking for is the values of z that separate these areas. And since our normal distribution is symmetric, we're going to have a negative z alpha over 2 and a positive z alpha over 2. Here's an example of finding a critical value for a specific value of our confidence level. So let's find our critical value for a confidence level of 95%. First, we need to find alpha. So alpha is just 100% minus our confidence level. In this case, that's going to be 5%. And we normally write alpha in decimal form, so that would be 0.05. This area is going to be split between the 2 tails, so we need to divide that by 2. So alpha over 2 is 0.025. So here's our picture again. Our confidence level is 95%, so that means we've got 0.025 in each one of our tails. What we're going to look for is these 2 values that form the borderline between those 2, or between those 3 regions. Now, to do this, we're going to use our calculator function inverse norm that we talked about before. And the easiest way to do this is to find the negative z alpha over 2 value. Because remember how your calculator function works, it assumes that you're going from the z value to the left. So this is the easiest one to find. All we have to do is put in our area in that left tail, which is 0.025, and this is the standard normal distribution, so our mean is 0 and our standard deviation is 1. If you put that in your calculator, you will come out with negative 1.96. So our value on the left side is negative 1.96. That means the value on the right side, which is the one we're actually going to use, is positive 1.96. So really all you have to do is take the negative off. Alright, so here's our picture with our two cutoff values. We have negative 1.96 on this side, positive 1.96 on this side. Now we're going to use all these things to find our margin of error for the confidence interval. So when data from a simple random sample are used to estimate a population proportion P, the margin of error, which we denote by a capital E, is the maximum likely difference between the observed proportion P hat and the true value of the population proportion P. The margin of error E can be found by multiplying the critical value and the standard deviation of the sample proportions. So here's the formula. Our margin of error is equal to our critical value, Z alpha over 2, times the square root of P hat times 1 minus P hat divided by N. Again, the center of our confidence interval is going to be the P hat, and the distance the interval spreads on each side is E, the margin of error. So our confidence interval will actually look like this. Our lower limit will be P hat minus E, and our upper limit will be P hat plus E. Here's an example. Find the margin of error in the confidence interval for a proportion if P hat is 0.35, N equals 400, and the level of confidence is 95%. Now we already found that the critical value for a 95% confidence level is Z alpha over 2 equals 1.96. For when we're working with confidence intervals for proportions, these values won't change. But once you have found a critical value for a specific confidence level, you can use that from then on. So our margin of error is going to be E equals 1.96 times the square root of 0.35 times 1 minus 0.35 divided by 400. Here we're just putting in the P hat and the N into our formula. So if we calculate that out, that turns out to be 0.047. So for our confidence interval, we're going to take our P hat, which was 0.35, minus 0.047 to get our lower limit. To get our upper limit, we take 0.35 plus 0.047. So our confidence interval goes from 0.303 to 0.397. The interpretation of this confidence interval is that there's a 95% probability, or we can say we're 95% confident, that the true population proportion is between 0.303 and 0.397. So here's the picture of our confidence interval. Again, our sample proportion, the 0.35 is right in the middle. Here's our lower limit, and here's our upper limit. And we're saying that we're 95% confident that the true population proportion is somewhere in this interval. Here's another example. In our Pew Research Center poll, 70% of 1,501 randomly selected adults in the United States believe in global warming. Construct a 90% confidence interval estimate of the proportion of all adults in the United States who believe in global warming. Again, what we're being asked for here is a 90% confidence interval for the population proportion. So first we would find alpha. Alpha is 100% minus 90%, so that's 10% or 0.10. Alpha over 2 would be 0.05. Then again, to find our critical value, we'll find the negative Z alpha over 2 and then just take off the negative. So that would be inverse norm of 0.05, which was our alpha over 2, with 0 for the mean and 1 for the standard deviation. And that gives us negative 1.645 on your calculator if you round it to 3 decimal places. So our critical value that we will use is positive 1.645. In this problem, we were given the sample proportion as a percentage, 70%, so we'll change that to a decimal form as 0.70, and our N, oops, sorry, typo there, our N is 1,501. So our margin of error is 1.645 times the square root of 0.70 times 1 minus 0.70 divided by 1501. And that turns out to be 0.019. So our confidence interval is, our lower limit is 0.70 minus 0.019, our upper limit is 0.70 plus 0.019. So our confidence interval is 0.681 up to 0.719, or from 68.1% up to 71.9%. And the interpretation of this is that we are 90% confident, or we can say there's a 90% probability that the true population proportion is between 68.1% and 71.9%. Here's a third example. In July of 2008, a Quinnipiac University poll asked 1,783 registered voters nationwide whether they favored or opposed the death penalty for persons convicted of murder. 1,123 were in favor. Construct a 99% confidence interval to estimate the proportion of registered voters nationwide who are in favor of the death penalty for persons convicted of murder. So again, the first thing to do is find alpha. Alpha is 100% minus our confidence level, which would give us 1%, or 0.01. Then we divide alpha by 2, which gives us 0.005. Our negative critical value is inverse norm of 0.00501, which would give us negative 2.576. So the critical value we use in the formula is 2.576. Our p-hat we actually have to calculate here. It's the number that said they were in favor of the death penalty divided by the total sample size. So it's 1,123 divided by 1,783. So that's 0.63. And our n is our sample size. So our margin of error, if we calculate this, turns out to be 0.029. So to get our confidence interval, we take our point estimate, or our sample proportion, minus the margin of error, and our sample proportion plus the margin of error. And that gives us from 0.601 up to 0.659 for our confidence interval. So the interpretation of this is that we are 99% confident, or we say there's a 99% probability that the true population proportion is between 60.1% and 65.9%.